Hello, everybody. It's time to start our fascinating discussion on the wonderful world of telescopes, the primary tool of astronomers. This is the first video of Unit 1, Part 5, our last part of Unit 1, our last bit of general astronomy. All right, so before we actually go into just talking about what the purpose of a telescope is, and you might be surprised because it's not magnification, I want to go ahead and start this video with just letting you know what kind of telescope facilities are out there. I can by no means list all the possible telescope facilities, but I wanted to just go ahead and pick a couple of the most advanced ones that are currently in existence and give you some upcoming, very, very exciting telescopes that are under construction and will be underway shortly. So here on this introductory slide, uh, we're going to be talking about the purpose of the telescopes and their basic design. And I want to show you what some of these professional telescopes look like. Let's start with our ground-based facilities that already exist. These are in operation, doing observations every clear night. All the telescopes I'm going to describe operate in the visible wavelength range and have a little bit of sensitivity either in the ultraviolet or in the infrared as well, but they're primarily visible light, so they're using mirrors. This telescope right here is the world's biggest pair of binoculars. It's called the Large Binocular Telescope, or LBT for short. It is in Arizona on Mount Graham, and here you can see the two 8.4-meter mirrors, and 8.4 meters, you're talking about 25-ish feet, a little bit shy of 30 feet. For each one of those mirrors, they are staggeringly large, and they're working simultaneously together as a giant pair of binoculars, which preserves depth perception. So absolutely incredible facility that's out in Arizona. And then we have my favorite telescope facility in the world, and arguably the most advanced optical system in the world, the Very Large Telescope. This is located in La Silla, or is it Paranal? It's in the Atacama Desert in South America, and it is four telescopes that can operate independently or in conjunction with one another in what we call an interferometer. And they operate primarily in the infrared, but also have some visible light capabilities. The telescopes, each one of them is 8.2 meters in size, so absolutely enormous. Here you can see the telescopes operating in the southern hemisphere. There's the Milky Way, and there's the two satellite galaxies of the Milky Way. And this yellow beam that's shooting out of it is actually a laser that's equipped on the telescope, so it can create an artificial star to start correcting for all the problems that the atmosphere causes to give us the highest resolution images of pretty much anything in existence right now. So, absolutely wonderful facility, already in operation and been revolutionizing our views of the universe for years now. So, these are the two that exist. The upcoming exciting ones, we have the Vera Rubin the Vera Rubin Observatory. This is also going to be located in South America. And this is a survey telescope where it's just going to scan the sky. It's going to do a complete pass of the entire sky every couple of nights and just survey, looking at everything that's out there, looking for changes from night to night to discover new things, transient objects like new asteroids, comets, things like that, and to get some of the deepest views of uh, our skies possible. This used to be called the LSST, the Large Synoptic Survey Telescope, and they're always sort of given a bland name at first, and then they get a cooler name. And this one was named after Vera Rubin, the discoverer of dark matter. Then we have the Giant Magellan Telescope, which is currently being built. I've seen one of the mirrors as the mirrors were being constructed in the Mirror Lab out in Arizona. This telescope is ridiculous. So you can see right here, you have a bunch of mirrors, right? You have three right here, and you can see the center one. It'll be a total of 7 mirrors, 6 around the outside, 1 in the middle, each one 8.4 meters across. So giving it an effective diameter, if you go from one edge to the other, of 8 times 3, about 24 meters. It's going to be the most powerful telescope of its kind, where it's using 7 super large mirrors. Notice that all the mirrors have been about 8 meters in size. This one is an 8.4 meter telescope as well. And it's almost as if there's some limit to how large we can make a single mirror, and some we're going to talk about in a future video. So this telescope is under construction. The mirrors are being polished and built. It takes a while to do all that, and it's pretty exciting. And then one of the upcoming space observatories, I debated whether I want to show you James Webb Space Telescope or if I wanted to show you another one that's a little bit lesser known. A lot of people have heard of the James Webb Space Telescope, the spiritual successor to the Hubble telescope, but it's going to operate in a different wavelength range, and it's going to be much different in design and much larger than the Hubble Space Telescope. But most people have not heard of the Nancy Grace Roman Space Telescope, formerly called W First. This telescope is using the same general build as the Hubble Space Telescope, a 2.4-meter mirror, and it's essentially a Hubble clone, except with 30 years more advanced technology going into this thing. And a lot of that comes down to detector technology. So this one is designed to operate very similar to how Hubble has been operating, except its field of view is enormous. So a field of view is how big of a patch of sky can be observed by a telescope. And this image right here, this is Hubble's field of view superimposed on a picture of the Andromeda galaxy. So that's the Hubble field of view. This will be the Nancy Grace Roman field of view, over 100 times bigger than the Hubble field of view. And it's going to have the same resolution and the same capabilities as the Hubble Space Telescope, but with 100 times the field of view. It's going to be amazing. I'm really, really excited. This telescope is primarily trying to study the earliest times of our universe, look back times of like 12 to 13 billion years old. So looking at the galaxies as they were first forming in our universe. Because remember, when we look at large distances, we're also looking back in time. So this will be looking at galaxies as they were first forming, because it's taking the light that long to reach us. Absolutely amazing. And since we're doing an astronomy class where we talk about telescopes, I don't have time to go through all the other amazing telescopes, the Gemini North and South, the Keck telescopes, the Infrared Telescope Facility on Mauna Kea, the SALT telescope, the Grand Telescopio Canarias. There are so many amazing telescopic facilities out there, both space-based and ground-based, that I could basically spend all week going over each one of those. I just want to give you a little bit of a sample so you know what professional grade telescopes and astronomy is like. It's not just backyard telescopes. All right, so what is the purpose of all those telescopes? And there are two primary purposes to a telescope, and neither one of them is magnification. It's not about making things look larger. It's about two other things. And the first one is about making faint objects appear to be brighter. The human eye is very limited in what it can see. We can only see about 9,000 of the stars that are up there in the sky with the human eye. There are still more stars, but they're too dim for the human eye to see. Our retina doesn't register that light. So one of the things we want to do with a telescope is we want to look at all the faint things. And I figured I might as well show you the faintest things that are out there. This does not include the faintest object, but right here is the what's called the Hubble Extreme Deep Field, the XDF. It's staring at what appears to be a completely dark patch of the sky. This is not the actual field of view. This is the size of the field of view compared to the moon for scale. But they pointed the Hubble Space Telescope at a dark patch of sky and then just gathered light for an enormous amount of time using the ridiculous sensitivity of the Hubble Space Telescope, allowing us to see all of these galaxies in this tiny patch of sky, where the faintest galaxies you see in this image are 6.3 billion times fainter than the human eye can detect. So if we want to study these galaxies, and here we have a look back time of 13.2 billion years. So if you want to know what galaxies look like shortly after the universe started, about half a billion years after the universe started, here's a picture of it. So we want to be able to see these faint things if we want to study these objects. So we need telescopes to make these faint objects bright enough for us to gather the light and then do all the amazing things like study the light, what the things look like, maybe do some spectroscopy as well, use that light to split it up by wavelengths. We need to detect the light to study the light. So we really want to make faint things look brighter. So that's job number one of a telescope. Make faint objects appear much, much, much brighter. How do we do that? We gather as much light as we possibly can that they're giving off. So we want to gather more light. What's the other purpose of a telescope? We have already done make faint things brighter, but we also want to make images be sharper. We want detail in the images. We don't want just a blurry mess. We want to see the individual stars. We want to see the details in the dust lanes of the Andromeda galaxy here. So here is a very high resolution image of the Andromeda galaxy. Here is the highest resolution image of the Andromeda galaxy ever taken. And I'm going to go to a separate thing and we're going to zoom in just to show you how detailed it is. But really, we want to make images really, 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 really sharp. We want to preserve all the details. We want to be able to say, there's a little tiny star there, and there's another star right next to it, and another star right next to it. We need to preserve all the detail as possible. We don't want blurry images. We want sharp, detailed images. And the term that astronomers use is we want the best angular resolution possible. So we want very, very good angular resolution. So let me go ahead and show you this really, really deep image of the Andromeda galaxy, this highest resolution image. So here you can see that same image I had on the slide, except this is the real image where I can zoom in. And notice that it just looks like this is sort of faint milky white, say in this region right here. So let's zoom in on it. As we zoom in, we see, whoo, that is a lot of stars. That is a lot of detail. We want to be able to capture that detail. We can zoom in further, and now you can see all of the stars. Some of them are red, some of them are blue, a lot of them are white. And we can go all the way in, and now you can see all those individual stars. This is the highest resolution, the sharpest image of the Andromeda galaxy that's ever been taken. So maybe we want to look at, say, what is going on with this dust over here. We want to preserve as much detail as possible. We want really good angular resolution. We want to preserve all that detail. And there's a really good thing. So our two primary purposes for telescopes, to make faint things brighter and to make images more detailed, preserve as much detail as possible, have really good angular resolution, as we say in astronomy. They're both accomplished doing the same thing with a telescope. Make the telescope as big as possible. Bigger means sharper images. You can control the details of the light by having a bigger collecting surface. And if you have a bigger collecting surface, you're capturing more light. You're taking more of that light and focusing it to our detector, whether that's our eye or like the cameras that we have in our phones. So that's going to be the name of the game, is making telescopes as large as possible. And finally, I just really want to hammer in that it's not about magnification. So here is actually a stunningly good amateur astronomy image of Saturn taken with a small telescope. I think this is with a, if I remember my details correctly, this was taken with a 10-inch telescope. So these are the kind of telescopes that you might have some friends that have telescopes of this caliber. They stacked a whole bunch of images together to get this image of Saturn. But yeah, this is a good image of Saturn with a small telescope. What happens though if we were to just magnify it, make it bigger? Oh, look, I got a bigger, blurrier image and the light spread out more, so every little bit of it is a little bit dimmer. That doesn't do me any good. I just have a bigger, blurrier, dimmer image. And that's not what we want in astronomy. We want brighter, sharper images. So in a lot of times, magnification, it kind of works against us in astronomy. It's great for public nights. It's great for sharing off the night sky. But a big, dim, blurry image is not very good for studying the universe. All right. So that's what I have for you. Oh, no, I still have some more for you about telescopes. So, what are our designs of telescopes? Sorry, I'm getting super excited with all this. So, a telescope, what is it? How do we build one? And the basic design is as simple as the one that Galileo made, which is basically a tube with two lenses at the end. Or we can use mirrors. So a telescope ends up being a collection of lenses and or mirrors which have a purpose. Those lenses are there to focus light, to take a lot of light and squeeze it down, concentrate it into a very, very, very small concentrated image. Squeezing all that light together makes things look brighter. So it is a collection of lenses and or mirrors which focus light, and then we take that focus light and we detect it. We put it on our retina in our eye so we can see an image, or we take a picture with a camera, either a CCD camera or a CMOS camera. So you're going to need, for a telescope to be worth anything, a detector. That could be your eye. Just put your eye up to the eyepiece. Or you could be fancier and take a picture using something like film, if you want to go old school, photographic plates, CCDs. That's the kind of cameras that are in a lot of telescopes, and it used to be phone cameras, but now some telescope cameras and almost all phone cameras. So the camera here in my phone, the little detector in there is a CMOS detector, and then that's pretty much it. You have a series of lenses and mirrors that concentrate light, and you send it to a detector. You put a tube around that, and you call that a telescope. Simple. Now we can get fancier, and maybe we want to take that light and pass it through something that'll split it out into the rainbow. And then we can measure how bright each color, each wavelength is. So we could pass the light through a spectrometer before sending it to a detector. And then you're getting some more fancy designs. And just to give you an idea, these are the kind of telescopes you're probably used to seeing. This is a reflecting telescope design. This is a refracting telescope design. And these are the kind of things that you might end up wanting to use. These are great for amateur astronomy. I highly recommend both styles, depending on what you're trying to observe and what your goals are. But just to show you what a professional telescope looks like, this is the Apache Point Observatory 3.5-meter telescope. So this mirror is 3.5 meters from one side to the other. Remember, that's about 3 feet per meter. So you're talking about 12-ish foot mirror right here. It's a little bit more than 3 feet. And then it focuses light, it bounces off this mirror, and then sends it down to the instruments and detectors down this pipe in the middle. But let's talk about the primary types of telescopes. And we're going to divide telescopes only into the two most generic types. That's all you need to remember for this class. That we're going to have our telescopes that use refraction to focus light, our so-called refracting telescopes. This is the kind that Galileo used. And then we're going to have our reflecting telescopes. They use mirrors to reflect light to focus light. And we have a couple of terminology things that you should be aware of for quizzes and exams and homework for each one of these telescopes. So here's our refracting design. Our refracting telescopes use a series of lenses only to focus light into an image. You have the main lens, which we call the objective lens, the big one that sits at the far end of the tube, and light will come in and it gets focused. And then we pass it through a second lens, an eyepiece lens, to make a nice clean image of whatever we're looking at. And this is the choice of your eyepiece lens that actually controls magnification. You wrap a tube around that, a telescope tube, and you basically have yourself a refracting telescope, often just called a refractor. That's how Galileo made his. He had two lenses and a tube. A reflecting telescope, commonly called a reflector, is a little bit different in design. And Newton was the first one to come up with a reflecting design for a telescope. So light comes in, we bounce it off of a curved mirror, which then tries to focus the light, but we're going to pipe it out the side of the telescope and use one lens, an eyepiece lens, to make a nice clean image. So this one's going to use a series of mirrors, one mirror here, another mirror here, and a lens to focus light. What kind of terminology do you need to know? Well, the tube that wraps up the entire telescope is still called the telescope tube. This big mirror that does all the reflecting is called the primary mirror. So this mirror right here is the primary mirror. And then we have a mirror. Because you can't put your head over the very tube blocking the light that you're trying to observe, you got to pipe it out the side of a telescope or a reflecting telescope. So you put a second mirror that bounces the light to the eyepiece over here. So you have a secondary mirror. That's this right here. So if you could see this, the front side of it, you'd see a very reflective mirror right there. And then you pipe it out the side for one design, or you pipe it right back down through the center, all the way down that way for another kind, which you can see in my more full notes on this topic. So I just want to show you, using the two images that I showed you before, this is what the telescopes look like. So this is the diagram of how light bounces around inside them, moves around in them, refracts or reflects, for a refracting telescope and a reflecting telescope. And this is what they look like in real life. This is a common refracting telescope that you could buy from Meade. And this is another Meade reflecting telescope. Meade is just a company, nothing special about it other than they make good telescopes. All right, so lots that we learned about telescopes already, and it's just going to get more fascinating as we get into the details of all of these telescopes. I'm looking forward to sharing all this information with you in videos coming soon to you.